Hello and welcome to part 6 of this video series. In the last video we took a look at how we can calculate the roots of n-dimensional vectors using the Newton's method. On this video we're going to take a look at Broyden's method, which is simply an extension of the Newton's method itself. So why do we want to use the Broyden's method? The main problem with Newton's method is that we need to calculate the inverse of a matrix iteratively, which means we might have to calculate like 50 different inversions of a function. And as our matrix gets bigger, the number of iterations also get bigger, and the computational resources required gets exponentially larger with that. So in order to avoid having to calculate the inverses iteratively, what we end up using is the Broyden's method. But sometimes Broyden's method itself is not sufficient to calculate our roots, because sometimes Broyden's method will just not allow our solutions to converge. In this case, what we'll do is we'll do some step-size adjustments, which will actually allow our function to converge. So let's take a look at what Broyden method is and how we do that in Python. So first of all, what Broyden's method tells us is that we can calculate the inverse of a Jacobian using this particular formula. So what this basically allows us to do is calculate the next inversion of the Jacobian by using the previous Jacobian, and in this whole process we do not have to calculate the inverse of any Jacobian as long as we have the inverse of one Jacobian. So yeah, since it's simply an extension of the Newton's method itself, let's just copy over our Newton's method function, and I'll paste it over here. So let's just change the name to Broyden's method. So first things first, we need the function f equal to 0. Again, Broyden's method will still use the Newton's method formula, which we have. Just as a reminder, Newton's method uses this function, x1 is equal to x0 minus the Jacobian of the function f evaluated at x0, take its inverse, and multiply that by the function at x0. So this is still applied in our Broyden's method. Also, this particular formula that we're going to use is actually called the Sherman-Morrison formula. So, first things first, we need f0, we need x0, and x1 and the Jacobian are to be calculated. So let's see. So first of all, we've got this, and then we have the Jacobian of the function, and we will calculate the very first inverse of the Jacobian outside of the loop, because we don't want to do this iteratively. So let's call it imv underscore jf. Oh, jf. And this would be, we actually have it right here. We'll just copy this and paste it. We are going to have to use a loop, so this loop is still going to stay, but this function will come out now. You'll be using it as inverse underscore jf, and this is pretty much the Newton's formula. And after that, we calculate f1. Again, we also calculate this, the magnitude of our f1, which we want to be as close to 0 as possible, in which case we want it to be lower than our tolerance. And then after we have this, let's write down our Sherman-Morrison formula first. So Sherman-Morrison formula says that J, the inverse of JF, actually I have this formula copied somewhere else, so I'm just going to copy and paste it. Let's delete that first and paste. So basically what we have here is our new inverse is equal to our old inverse plus delta x minus the old inverse times delta f, and we do a vector multiplication with the transpose of delta x, which is vector multiplied to our old inverse, and all of this is divided by the transpose of the delta x, which is vector multiplied to the inverse of the old Jacobian, and which is also vector multiplied to the delta f function. So let's define our delta x, which is simply x1 minus x0, and then our delta f would be f1 minus f0. Once we do that, we're just going to say that our x0 is, we're going to update our x0 value with the newly calculated x1, and we're also going to update our f0 value to the newly calculated f1. So we save that, and let's try to see what result we get just by using the Broyden's method. So Broyden, and our function is, we're still going to use the function that we used in the last video, this one. And okay, our x0, I'm going to use an JMP array of 2 dimensions, 0, 0, and 0, both being integers. And yeah, that's all we need to supply to this function, so let's try to run it. Okay, we get the result, not a number, not a number. So let's see what went wrong. So what I'm going to do is, under this for loop, I'm going to print, and I want to see what our magnitude of f1 looks like. So we'll paste that, and I also want to see just how many iterations we ended up doing. So I plus 1. So let's run that, and then run this. Okay, so it looks like we ran all 50 iterations, which is the upper bound of the amount of iterations we're allowing this program to run. And if we look at the magnitude of f1, what we see is that it's kind of stuck at a certain value, and suddenly it starts to explode to a really big number. We see that it's in the magnitude of 10 to the 81. So that's a big number when what we actually want is for the number to go to 0. So how do we fix this? So like the first thing that we can actually do here is that we see that our number is getting larger. We can just simply prevent that from happening. So what do I mean by that? What we can do here is, while our magnitude of f1 is larger than the magnitude of f0, what we do is we set the difference of, we scale down the difference of x1 and x0. So what I'm going to do here is, instead of having calculating x1, I want to calculate delta x, which is basically x1 minus x0. And of course I do still need x1, so I'll set that here as well, which is x0 plus dx. And then I'll set an multiplier, I'll call it alpha, and I'll set that to 1 for now. And every time our magnitude of f1 is larger than f0, what I'll do is I'll multiply our alpha by 0.75, so times alpha. And what we do from here is scale x1 to be equal to x0 plus our alpha times delta x. And using this, let's make that a little clearer. Yes, so using that, we calculate f1 by evaluating f at x1. So let's do that and see what results we get. Here I also, okay, now let's just calculate that first. Okay, we're still getting the same error, but this time our magnitude of f1 is actually approaching 0 instead of exploding into a really big value. So it's still not what we want it to be, so let's take a look at what the problem is. Yeah, on top of looking at the number of iterations and the magnitude of f1, I also want to take a look at the value of alpha, because that's the only new thing that we introduced, so the problem might just be there. Okay, so let's see what we get here. Okay, the pattern that I see here is that we start with a alpha of 1, and then we go to 0.75, and then it just explodes into a really small number at the magnitude of 10 to the negative 16. So yeah, let's figure. So what can we do here? Now, what I can think of doing in this case is that if our alpha value becomes smaller than, say, 10 to the negative 10, our tolerance, we might as well just recalculate our inverse. Remember, the problems that we're actually trying to solve is that we don't want to calculate the inverse of our Jacobian iteratively at every step, but we still want to make an exception where we are allowed to calculate these inverses sometimes, only when necessary. I would say this is a case where like calculating the inverse is actually necessary because our solution is simply not converging. So let's do that. So what I'll do here is I'll go down here, and if alpha is less than our tolerance, I will say our inverse is recalculated. Even though I'm copy pasting this value, it's still a new value of x0, so there won't be any issues. And after that, we want to recalculate the value of dx. And yeah, that should solve all of our problems. So let's run that and run that. And yeah, there we go. In 26 steps, we calculated the roots of our function, which is right here. This is also, we know that this is true because we already proved it using Newton's method, and we got the exact same value.